Welcome to Renaissance Charge videos. I'm Rick Friedrich, and today we're going to talk about negative energy again. We're going to look at charging batteries to make them negatively charged. It's a very complicated subject. It's not what people are used to. So I've decided that I'm going to go back in that direction. So I'm going to talk about that today and the different processes and the effects that you can get as we have done these kind of charging of these batteries for years. So let's go over a summary of what we're going to talk about. We're going to talk about, first of all, reconditioning batteries. We're getting brand new batteries so that we don't start a conditioning process, which is another stage in converting the batteries over to negative. But we want to rejuvenate the batteries first. So we'll talk about that first. Secondly, we'll talk about how long it takes and how you do the conditioning process. And we'll talk about what it means to be negatively charged at some point. And then we're going to talk about how you can make a negatively charged battery, which we talked about in a previous video, I think 2 videos back. If you look at the video where we're talking about negative energy, negative series impedances and so forth, that this is necessary to go with that video to really explain what it means, because I've been talking to people for years about this, and most people just don't get it because it really takes experience to see these things for yourself. Really, I don't really believe anything that I don't have solid evidence to believe or that I haven't witnessed myself unequivocally. So then we're going to talk about how I've changed the motors over the years, and that you can do this process with any of the motor systems, and I'm going to show several of them today. And then we're going to look at the particular upgrades that you could use to convert your motor that you have. So once in a while I find people that gave up on the SSG circuit, which was called the Simplified Schoolgirl circuit, after a 10-year-old Shawnee Bowman who won a science fair back in the year 2000 with that circuit, well, with the schoolgirl circuit, so it was nicknamed that. It was in fact an old circuit that was patented back in 1974, and it was the top spinner patent that was using that circuit. And I think Bedini learned about it in 2000 or 1999. So someone has passed on that information to me. I can't confirm that. Nobody really can right now, but he then, of course, brought it out to the public, and especially through this girl, and who won the science fair award. She had a motor spinning. We're going to look at a very similar motor to that, where she had it spinning for a long time, and the battery should have drained. It lasted over the whole science fair, and it should have drained in that time, and it didn't. And it really could go for several months without discharging. And I've talked about that in the past. It's not terribly important, but historically, Bedini gets the credit for the circuit, even though it was patented a long time before him, and so forth. But anyway, I also made the circuit popular through numerous email groups, which Bedini eventually shut down after we parted ways. That's another long story. You can look at my videos 2 years ago where I talk about that. Anyway, we'll talk about the various motors and what it means. And So let's start off. That should do it for now, for the introduction. So let's start off with battery rejuvenation. So I'm going to be charging with this small motor, very big battery bank to get maximum gain. And we'll talk about why and how that could be possible, where you get much more output with a larger battery. But right now we're going to start off by talking about what you want to do with the battery first. So most batteries get sulfated and damaged over time, so that you have to replace them in 3 to 7 years approximately. They start losing their usable capacity right away. In fact, a battery that sits for even 4 months unused will start to sulfate and develop some sulfation buildup in that short period of time. So we recommend, I'm not trying to push a product here, but starting off this process with a clean battery. And so you can do that by even starting with a brand new battery that has the date stamp on it with that month, so you know it hasn't been sitting for a long time. Batteries can sit on a shelf for years, well, not usually years in the stores, but I've seen them sit on the shelf for they're a year-old battery. So maybe they weren't delivered right away, or maybe they sat on the shelf. And so then they sell these off. So after a battery's been sitting for a year, it's going to lose, pretty much after 6 months, it can lose half of its capacity through sulfation if it's not a brand new battery, but if it's older battery, if it sits for 6 months. But a battery that's never been used and sits for a year could be lose more than half of its capacity, usable capacity at that point, because it's sulfated. So a battery that's charged with regular charging, including an alternator in a car, or just all the types of chargers that you find out there, will, especially constant current, but even pulse chargers, will develop sulfation, or the pulse chargers will damage the plates of the batteries in trying to desulfate them. They'll also de-lead the plates, if you will, and send everything to the bottom of the battery. We don't do that. We dissolve the sulfation and we bring the battery back to its new condition. There's also a conditioning process with the battery chargers that is allowing for, especially an older battery that has already been sulfated and the plates have expanded, to gain in capacity through a conditioning process that happens in the battery. It's like a foaming effect, where the battery gets more surface area because it's been puffed out. And so as long as it doesn't crack off and fall to the bottom, which it's in danger of doing if you put a hard load on it, or if you do hard pulse charging to it. And that's what a lot of companies do, because they don't really understand how to properly rejuvenate or charge a battery. So we've been doing this. We've been selling these chargers for 12 years commercially all around the world, in which this unit, for example, is our industrial model 3812, RC3812, and it does your small, medium, and large 12-volt batteries. This particular one is just a case, and the label is showing a 24-volt model. So we have 4 models of this, either 110 or 220 input from the wall, and either 12 volt or 24 volt only. There's no 6 volt or 18 volt, or you can't charge a 12 volt battery with the 24 volt model because of the transformer hookup and all that, and the programming. Anyway, what happens is in this unit, we cycle the battery, so it discharges the batteries down and charges the batteries up in several cycles before it becomes rejuvenated. Each cycle brings more capacity instead of the opposite, which you normally experience. In cycling a battery, you lose time, and everybody's worried about how much times they cycle the battery, how deep they discharge them. We don't worry about that at all. In fact, right now I'm discharging the batteries here down to 0 volts, and I'm doing that for 2 reasons. One, I'm removing all the positive energy out of the battery, or I try to do that each cycle until I can remove it. The other reason is I'm just deeply discharging it, so when I charge it back up, I'm going to really get to the full spectrum of the plates and fully condition them. So we do a conditioning process also with this, but it's more of an increase of capacity conditioning. So we cycle the batteries several times, and 3 to 5 times on an old, 3 to 7 year old battery or older may take a little bit longer, a few more cycles. And then we have the computer readout that you can see on the back here that connects to your computer, in which you can monitor that and save it in a file. Anyway, I'm not going to talk about this one too much, but it's important to rejuvenate your batteries before you begin this process. So again, people are using these chargers all around the world 24/7. These have been built to last, so people have had these chargers for 12 years, using them daily, doing thousands upon thousands of batteries in all areas of the world. So I'm proud to have that as a product. It's worked out great. So that's the first stage. Then I mentioned that we're going to discharge the batteries and charge them up. So I have here, I'm going to show the camera coming down here. So what I have here is a big coil here, just to make a quick resistor. So I have 100 feet of wire, which gave me, at 12 volts input, it gave me the 12 volt battery bank discharging gives me about 60 amps. So what I did is I just discharged each battery cell to make them even, and then I finally discharged them again. So you can see right now the voltage is it's just under 1 volt. So that's good enough to do this. And the second reason why is why I want to show you how the battery bounces back up in voltage once we disconnect it here. So let's disconnect it and see what happens, and remove this out of the way because we're done. I wanted to balance the batteries out so that they're all equal with each other by discharging them first. Discharging them first with by themselves, and then stringing them together in parallel. All these batteries are in parallel with each other. Okay, so we don't need to look to the ground, but you can see now they are bouncing back. I'm not going to hold this thing straight. So they're coming back up in voltage, but they are fully discharged as much as they can be. So each time we're going to charge them up, we're going to fully discharge them. And let me talk about that. Let me just move the camera back because we don't need to look at the ground. Normally this setup is for the big 4-pole here, but I'm going to show the smaller one for several reasons. So we don't need to look at those. I'm not going to try and prove anything here. I'm just talking about the process. In fact, I never try and prove anything through a video. They're just informative. Take them as you like them, or take take it for your own information. Whether you believe things or not, it doesn't matter to me, because I'm not trying to ask for you to believe me. But anyway, this is what I've done. People have asked for this, so I'm telling you. So one way to discharge a battery bank down to monitor it is to have a bulb. So here's a halogen bulb, so it can put a good 5 amps of load on it. You could also hook up the bright lights on there. It may get too hot though if you do both of them at the same time, because that's not really how your car runs, I believe. I should know as a mechanic. Anyway, so if you have the bulb and you just keep discharging the battery till it gets down till the light goes out, then you know you don't need to discharge it any further. That's as far as you go. So if any of you have seen my older videos, or some of my videos, or come to my conventions, you'll see I'll have a battery that says negatively charged. So I have 4 of those smaller batteries that I bring around to my meetings, and these have never been charged, except for maybe at the factory when they form the battery. They've never been charged by me since I bought them brand new with regular constant current or any kind of regular charging. So then what I did was I charged them. I did this individually with each battery, and I used one of my motors that we'll talk about in a second to charge them up, and then fully discharge them with actually this very bulb. And so then once the light went out, I would charge it back up. I'm not at all trying to look at efficiency, but it is something that you could start measuring to compare. You could look at the voltage amperage over time and see if you might find some interesting results. So we do that 10 times before we start really taking it seriously, what the output can be, and running regular loads off of those batteries rather than just going down to 0 or 1 volt or whatever it is. So that's the process to do with a certain type of energy, which is negative. So conventional theory has it as calling it negative energy, and it's the opposite of positive. But it's not really talked about or well understood, especially in relation to batteries. So there are very few people that really understand this unless they have done it over the years, which I have done many, many times for many years. We talked about Tom Bearden talking about this, and some of the information that he received was from me, and people like John Bedini was the primary source of Bearden's information on that in the battery. So it's quite useful, some of the things that Bearden says. Half of the stuff he said was really quite crazy, wasn't true. So it's kind of hard to decipher between what is real and good information and what was not. But the battery charging stuff, the negative energy stuff, it really works. Whether the physics is explained properly by him doesn't really matter too much to me. So we're going to talk about that. So let's look at some of the motors that I have sold over the years, in which this is one that we came up with, which we called the 3-pole monopole. So you have the motor coil at the bottom here that has a bifilar coil, and so the 2 wires are wound parallel to each other, and then one of the wires, the smaller wire, is the trigger wire. And this could be run as a 1 battery system if you only use it at about 9 volts with the right transistor. And that's what Shawnee Bowman did, this original schoolgirl, and 2000. And then the simplified version, it was called simplified after that, that had a 2 battery bank system. And so this way you could charge a battery up while you're discharging the other one. Now, the problem was that the energy needed to create the negative charging, not just to run the motor here, this is to create the negative charging, has to be a positively charged battery. It's just the way the energy works. So if you get a negatively charged battery that has become fully negatively charged, it will really not charge a second battery on a system like this. So what happens is, I should probably have said that a little bit later, but let me go back to that point another time. But for now, we have an input, so we have a basic circuit with a transistor, a couple of diodes, and a resistor. The neon bulb is just to indicate the charging battery is disconnected. It's not supposed to be on, like some people think. It's a very simple circuit. There's not much to it. It's very easy to make. And so this particular coil at the top here is just a generator coil to use as a load, and I use that to light up the whole thing. And this I'll talk about in a minute. So what happens is, as the battery provides power to the motor, the transistor turns on. In this case we're using a transistor, in that case we're using a MOSFET. As the transistor turns on and off, both on and off, at that moment there's a pulse, a negative pulse that goes to charge the battery through the diode. And the batteries are actually in series with each other, and the charging battery is rectified across the coil, across the motor coil. So the battery is not supposed to be able to be charged in that what's called a floating ground position. So the ground terminals of the batteries, the negative terminals, are not tied together. The batteries are in series with each other. So this is called a floating ground, and floating grounds are well known in circuits. In fact, all inductors really have a floating ground terminal. So anyway, normally that energy, negative energy, when the coil is turned off, that's usually people only consider when it turns off, but it's also when you turn on the circuit that there is initial event that takes place, a form of energy takes place that is not well understood, of course, that will charge the battery as well. So there's 2 switches. If you think about it as a switch, when you turn on the switch and you turn off, you're both flipping a switch. When you have an inductor, it has an impedance to it. It resists current flow. So at the moment that you turn on the switch, that resistance creates an event. It is an event which creates a pulse or a spark somewhere. So if you have a battery and you connect it up to a load, you'll see a spark, and that's before the collapsing of the coil. Okay, so people always focus on the collapsing of the coil. It's not a big point that I'm trying to make here, but when you close the switch, you can have sparking, and when you remove the switch and the coil collapses, you also have another switch, which most of the people focus on that. So either one of them creates a negative event that, if it's not dealt with, can destroy the transistor with a huge spike, high voltage spike that can be hundreds, if not thousands of times more of the voltage from the input, depending on various factors, like the coil and the speed in which you're turning the switch on or off, which is what I talked about in the previous video a couple of videos ago, which is very important. The rate of change determines the amount of negative flow, and also that's standard Faraday theory of in relation to inductance, and if you have a transformer, the faster the rate of change, the more energy is transferred and manifests, so forth. Anyway, that's not what I want to talk about specifically right now, because I've already dealt with that in another video. But these motors are really not motors at all, and that they never were intended to be a motor. They were always intended to be a mechanical oscillator. And of course, Bedini did not invent the monopole or these back EMF motors at all. There's prior patents and prior art. Robert Adams did a monopole before Bedini, and he wasn't the first either, although he believed he was. Nevertheless, the Bedini got a patent on it, and he called it a mechanical oscillator. And I worked with him for many years, and this is why I put the Bedini logo on this, just to make him happy. He didn't ask for it, and he didn't want these kits actually either, but I did them, and he went along with it. At least for a season, at least for a couple, well, at least for about 5 or 7 or whatever years that we did this. Anyway, so these create a negative pulse when you turn on the switch, turn off the switch on the transistor, and then this battery then receives a charge and becomes a negative resistor. So what we found was that people wanted to rotate the batteries, and because, as I said, you can't, when you fully converted a battery to be negative, you cannot use it to power the motor. Now, I haven't shown this, I've only talked about it sometimes, but we can reverse the motors to run off of negative charging, a negatively charged battery to produce a positive charged battery. I've done that at times. I'm not going to get into that, but there are various processes. So one of the processes we used to make the battery not negatively charged was to put a capacitor before the battery being charged and then pulse that capacitor into the battery. The capacitor converts the negative energy back to positive energy, and so the battery then could be rotated with the charging, and the run battery could be rotated. I've done that most of the time with my demonstration models or my big motors. I had a boat running that way for 3 years, a 26-foot cabin cruiser boat that I ran, and I just rotated the batteries. I didn't need to charge the batteries, and it was using this other motor right here. I'll show you in a second. So actually I can show that. This was the other motor that we still sell, and it was called the window motor. It was really a design that Newman partly came up with. This is a different design than Newman's motor. Joseph Newman, Beard and Bedini copied Newman's work, and didn't really, they gave him more credit at the beginning in the 80s, and then by the 90s and 2000s, they, for various reasons, probably due to his personality too, that they didn't really give him the credit for this type of motor. Now, Newman probably didn't invent it either, and both Bedini and Newman wrapped the coil all the way around, and around, like on the either side of the shaft. It was not really practical, so I always ran it this way. So you have north-south facing magnets, and you have the either coil side will be directly over top of opposite magnets, because you have a spinning taking place like this that rotates, and that's the motor side. The circuit is the same as the other one, and it also creates a negative charge. Now, we have always sold this, so it's a negatively charged battery. And the reason why, so the boat was made with this type of motor, but the motor was 300 pounds. The coils were 60 pounds each. They were huge. Anyway, I have one motor that I still sell. Right now, I don't have any inventory on it, so I've kind of temporarily discontinued it. But we have made that as a commercial product that people have used for boats, especially, or generators, self-generators, energizers. So anyway, the energy ends up changing this battery. And what we were intending with this before I came along, the intention of these kinds of systems were to do negative energy engineering, which is totally opposite in pretty much every respect to positive energy engineering, which is what everyone's used to. So it's very hard for an engineer to come to grips with that and do that and recognize that, because most engineers and people are not scientific. They are copycats. They follow an instruction from somebody, and they don't really think too much about what they're doing. And that's not insult, that's just the way people are trained. That's the way they're used to things. So when they have to rethink something completely different, it's very hard from them. So it's actually easier for people to learn this stuff right from the beginning before they get electrical engineer's degree or study anything along those lines. Unless they're taught physics the right way, they're going to be told this, you can't do this, and you can't do that, and this is the only way. And the truth is, with most of the sciences, what you're taught at the beginning is not what you're taught later on. It's just for convenience that you're told the simplistic things. And so over the years, people discarded processes that people weren't using, and then eventually became kind of like the tax code. It became a law that this is the only way to do it. A law in the sense of a law of nature in people's minds. And really it's just a certain set of circumstances that we're accustomed to doing that we experience this phenomena. But there's an opposite phenomena a lot of the time. In the spiritual world, there's a spiritual goodness and spiritual evil or badness, and these are opposite characteristics of character and opposite phenomena that exist. So in science, there's often two opposites, and in this case, we're talking about positive, negative energy. So you have the, if we're just going to focus on the collapsing of the coil, we have this build up in the inductance, which then collapse, and it goes in the reverse direction. So why is that? That's another subject that I don't need to get into. But the fact that it's called negative is probably for convenience sake. And I think most engineers don't realize that this is really a fundamentally different kind of energy, and it's very useful. In fact, it's quite more useful than the positive energy, because the positive energy, as everybody knows, dissipates over resistance. And so you have losses. You always have losses on the electrical side when you're using positive energy. You have a closed loop that discharges itself because it kills its source charge. So you have a battery that becomes a source of energy, and it has two potentials, and when you loop it around, it discharges itself because it's shorted out. And so you don't need to understand all the details of that. It's just common knowledge. People know it. And people always expect to have a loss in a closed loop circuit. That is only when you are considering the laws, which are only really rules, only apply to the fact of when it is constant current, in which there is no surging or pulsing or opening and closing of the circuit. Once you open and close the circuit, it no longer follows Ohm's law or Kirchhoff's laws. It is no longer subject to those under certain conditions. And these are not unusual in electronics. So people should never look at it as if we shouldn't focus on it. In fact, most people who study it study how to prevent it, how to limit that negative energy pulse and those gains that they experience, but they don't use it as a gain. So it's not truly a gain. It's a troublemaker in the circuit. It can destroy the circuitry. So many dampeners are placed to prevent all this kind of phenomenon. And that's the opposite of what I do. I focus mostly on the non-conventional side of things and try and design systems that can give you a gain, give you an advantage that's always ignored in regular electronic systems. So what are some of the details about the negative energy? First of all, on the negative side, or the weakness of the system, is that once it's charged, it will, well, I should say this is not a negative, but the result after this period of time is negative. So when you first charge the battery, it will continue to charge for a period of time depending on how converted it is over to negative, and how the intensity of the charging rate. The battery will continue to charge. Sometimes, some cases, we've seen them continue to charge for 24 hours. And that's kind of hard to explain how to determine that, but once the battery stops charging, then it actually starts discharging. So it's going to continue to charge for at least 15 minutes or so after you've stopped charging it. So what happens is it will slightly start to discharge much faster, though, than a positively charged battery. Positively charged battery will hold its charge a lot longer, but it won't really continue to charge after you've stopped powering it to charging it. So it's quite different in that regard. So both beneficially and the problem with it, like I said, is it can discharge itself pretty quick. The advantage is that it can continue to charge for a good period of time after you stop charging it. And this is where the rest period comes in. If you actually set up multiple battery banks and you charge them and you connect them in and out of the circuit, like we're going to do here. I'm not going to do that, but we're going to be charging only one battery bank instead of multiple at different time intervals. But if you do that, then you could take advantage of the rest period that will keep charging the battery. And in fact, every pulse has a rest period between the pulses. So this means that you don't have to continue to charge with constant current, and you have an advantage when you're doing a negatively charged system. The positive charging is not advantageous for the battery, but every time you pulse a battery, you're giving it some negative charge, and that's where it's getting its benefit from, either in rejuvenation or in gains in capacity because of the pulse. So there's a negative preceding the positive current flow. And this is what they found over 100 years ago when they ran the power lines, and when they turned on the power and the energy the dynamos connected up to the power lines, there was this instantaneous lightning bolt type of sparking that would come off of the line, not just at the switch, but way down the line before the current could even be able to be down the line. So there's an instantaneous, they say faster than the speed of light, switching and powering on the negative side that precedes the current flow. So in the presence of current, there is no more negative. It's done with its job until the next pulse. So the longer the on time, which is what we're going to get into in a minute with this motor, the longer the on time, the more positive energy, the constant current is taking place in a motor. So this is not really what we're after when we're negatively charging a battery. And that doesn't mean that the positive energy is necessarily going into the charging battery, because it's not in a position to be rectified to do that while there's constant current flowing. So it's only when there's a changing magnetic field that you can have any kind of, and here we don't have a secondary, but in a secondary of a transformer, it's only when there's a changing magnetic field that you can have any power manifesting in the secondary. So the changing magnetic field, it's not electrical phenomena, it's a magnetic phenomena. And so once the current stops changing in the motor coil here or a transformer, then you have no action of a beneficial nature. So in this case, we're after the pulsing rather than any current flow. So the longer we turn on our coil, the less efficient the motor has been. And that's really how I've run the motors for the last couple of years, which give you very little charging benefits, not benefits in the efficiency benefits. So I'm really kind of moving back towards doing the negative energy engineering as we've talked about the third stage process, which is series impedances upon the negative path, along the negative path, along the negative path, not the motor side of the circuit, but the output side. So we want to run series impedances there that take advantage of this negative high voltage spike that is coming back, and rather than take a lot of energy to move a motor, we want very sharp, abrupt pulses. So what Bedini did along those lines is he took two magnets. He was using the ceramic Briggs and Stratton magnets mostly to do this effect, and he pressed them together so that the north poles were facing each other and glued them together, and put them in his 10 coiler, and it's created a super pole. So what happens is there's a very sharp turn on and turn off, very sharp pulse. And he also used the trigger coil like I showed in these motors, which also allowed for that, a very sharp leading pulse. So then it except it's a negative pulse, not a positive. So what happens is there was a very great rate of change, which Tom Bearden talks about being necessary. The greater the rate of change, the more energy will manifest, which is conventionally believed as well on the positive side, but especially with the negative energy. So you have to constantly realize what is similar between the positive and negative energy and what is quite different or opposite. So the very fast switching on and off gives you the goods. Now that's not necessary because we can turn on our MOSFETs very fast. In fact, I'm going to be talking about that in a minute, where we're using, you know, as low as 4 nanoseconds of switch time and rise and fall time, very, very short periods of time here, and this creates enormous surge of energy from the environment. It draws in electrons, and it's very similar to resonance process, which draws in more electrons into its vicinity. So it does do resonance in the coils, will ring at their natural frequency, more or less, depending on their core material that you're using, will be more or less of a dampener or enhancement. So you can have, whenever you have resonance, you have a pulling in of energy from the environment. And so we want to do that fast rate of change, or the fast frequency. And so we can, that's what we're going to do with the motor, is really speed this thing up very fast and have a very short on time. So we don't need what Benini called the scalar poles with the 2 magnets pressed together. It's rather inconvenient to do that. It'd be quite difficult with neomagnets to do that and hold it. We've done that before, and it can be very dangerous to try and do, and I've crushed my finger to where it almost came off, and all the bones were completely crushed, and now it's back to 100%. I can't tell which hand it was, but anyway, I've experienced that, and it creates a very uncomfortable feeling when you're working with those big magnets after you've had that kind of accident. So I use safety. But anyway, we can create, even with these relatively big magnets here, these are 1/2 inch by 1/2 inch round magnets, way bigger than they need to be. But what I was doing with these magnets was trying to focus on the positive energy with the generator coils, trying to produce some real output with the generator coils. It never really turned out as good as I wanted to, but I really initially started those generator coils to show you when you short them out, the motor speeds up. And when you run, like what I'm going to do here, the output of the generator coils is going through this variac, and the variac is only at 13 volts. So the motor will still speed up until I get to about 25 volts. Then it will not speed up or slow down. It will just be the same as if I didn't have a load on it at all. And so the first 25 volts on the variac, when I do that, still allow the motor to speed up under load. Once I go beyond that, then I'm really using the generator coils as a generator. But what I was doing with those, it's not part of this video, but when the motor pulses, it creates an EMP, and so the generator coils pick up that pulse, and that's that 20% of the energy that is being used for the generator coils. So that's all I really intended was to make the motor speed up while it was providing a load, because that was a very unique thing that people really hadn't focused on or seen very much of. And so I wanted to teach on that. But then it became, well, it's really, instead of having an attached generator for a load for these, it became, let's load down with the generator coils too. So, but that really didn't turn out, it still didn't load down enough. Well, depending on what kind of load you did, it wasn't really desirable. And I never really wanted to create a generator as part of the motor. I wanted to focus merely on the batteries and the battery charging. And then I did, because I was a mechanic, wanted to make some motors that would actually run mechanical loads and get the beneficial charging while I was doing it. So I kind of had my own reasons for doing it. People wanted these systems, but really the real jewel is the negative energy. And so we're going to focus on that from now on, and really move away from all that. And I have no more coils left here, so I have to change the motor anyway. So I'm doing this video for all previous buyers, and there's a lot of people are waiting on their order right now, because I've been trying to decide really what to give them. And so I'm going to talk about options here for people, and the direction I'm going, and explain why the difference is. So at any rate, these coils aren't being manufactured anymore, so I have to have a new coil system. I may make smaller ones or bigger ones, and I haven't decided that yet. And the rotors may also become smaller if I go in a certain direction. So I'm still trying to decide some of that, but one of the things that I'm willing to show here, I may include with the kits that are still to go out, the remainder of these kits that we've sold up until this day. So what's the difference? Again, the positive and negative charging. So you'll be able to incorporate what I'm talking about with any of the previous motors, either by just changing the circuitry and choosing a very short on time. So what we're looking at is when you run it at higher voltage, there's less amperage. And so with this particular motor, if I'm going to run it at 48 volts instead of 12 volts, I have to turn down the potentiometer, which is a variable resistor, the little blue one on the board there. So I just do that with this little screwdriver, which I'll show you in a minute. And that will change or shorten the on time. So even though you have a big magnet passing a relatively big core, you have you can control the on time, in which the Hall sensor here on the top is positioned just really, depending on the voltage you're running it at, just before top dead center or after top dead center of the magnet. And so at startup, though, at the higher voltages, you have to really retard the timing, and then as it gets up to speed, you'll have to change that. So to run these, I really only sold this present model to do 12 and 24 volts, because after that the change requires quite a bit of adjustment of the Hall, and that's where I've done the double Hall, the startup Hall, and the regular run Hall. So anyway, you have the once it gets up to speed, which if you're doing 48 volts, will be very fast. So at 24 volts, with the double stacked model, which is really two of the same, sharing the same shaft, it can get up easily to 10,000 volts when the spacer in there is double spaced. Right now I have it double spaced When it's single spaced, it's a pretty powerful magnet lock, and it makes the motor pretty powerful. Easily can run at 100 watts per 12 volt division of batteries input. So you can do 100, 200, 300, 400. But I've never really set it up to run 36, 48 volts. We've run it up into the hundreds of 100 volts, over 100 volts, and it works really well, but we have to really limit the on time. And that's exactly what we want to do. That's really, when I made the big 10 coiler, the first model of it with the monopole, just like this model down here, but with 10 big coils, like we see the coils on the big motor on the ground there. The same basic system, but it had only one rotor, and now we do 2 rotors. Because if we're energizing the coil, we can actually, we have the magnetic output on both sides. So you might as well push 2 rotors than one. That's why I call it the dual pole. But the first model I actually made to run 120 volts is really what I was designing it for, but nobody ever wanted to run that high voltage, so they missed the real purpose of the motor. And maybe because I was demonstrating it at low voltage just for convenience sake, and I never got around to doing that that video, and I realized that people just didn't want to run it at that voltage. But really, I really should have more carefully focused on the negative energy and run it at the high voltages, because that's where you'll see the major gains. Now the problem is you have to have a suitable battery bank to be charging, otherwise it will blow out everything. You have to have, if we run it at that high voltage, we actually have to have transistors that are in the thousands of volts, and the same thing applies here. If we go up to 48 volts, we're going to have to, I have some MOSFETs that are 1700 volts. What I have right now is 900 volt MOSFET on there, rather than the 100 volt one right here, what we normally supply. This is a very good transistor, or a MOSFET. It's the best one you can get for resistance. It's one, or this one is 3 milliohm resistance, and that's very low. So it's hard to find the low resistance as well as the fast switching, which is both. Anyway, what we did again was focus on more positive energy and more torque, more output, because that's really what people wanted, and they were generally happy with it. People are, you know, several thousand people probably have these motors now, and I don't really hear too many complaints from people other than my mistakes in manufacturing. I had a kind of a mix-up with some of the rotors at one point, but it's been a pretty good motor. It's a really good learning experience from it. But I'm saying that I'm showing this video right now to really do a recap of everything for those who have had the motors and want to do something different or get more out of them. I'm explaining here how you can do that. So let's see here. So what I'm trying to move towards is creating the negative charging. So we have to do that with limiting the current flow in the coil. So we want to really just turn on and off the coil as fast as possible, which is not giving you very much motor action. And that's what the 10 coiler, original 10 coiler was. It didn't have any torque whatsoever. It didn't really have a lot of speed either, because it didn't have the ability to build up speed with the lack of current flow. So it was just basically turning on and turning off at a very sharp pulse. So we do that with the gate driver, turns on and off the transistor very fast. So we have a very sharp square wave, but we want to reduce it to more like a triangle wave without the triangle. So we want to just create this. So we're going to look at that in a minute. I can only do that so much at 12 volts because I'm really setting this up to run at 48 volts, where, but I can't use that MOSFET for 48 volts without creating another flyback diode dampener system, which I'll talk about a little bit later. So what we want to do, I'll talk about it probably next here. What we want to do is create very, with a higher voltage input, we only need a little bit of on time to get the motor rotating. So you have a lot less loss in the system. You get always more energy gains in the higher the voltage, especially in a resonant system. But here we're not really focusing too much on resonance. There is a resonance process in the batteries, but not really in the coils here, the way we're running them. There is some damp wave that you can see on the oscilloscope, which we'll look at in a minute. But anyway, you have, with the on time being very short, we have the more desirable effect where we have more pulses and less energy wasted to as a constant current closed loop situation. So we want, you know, the rising and falling to be as sharp as possible, not necessarily as frequent as possible, because the battery continues to charge at rest periods. So ideally, like when we did the pendulum examples, this has a certain advantage because there's quite a big delay between each pass. Now there's multiple oscillations when the coil passed, but there was this rest period, and this gave you quite a interesting charge in the battery because it was resting, but it was continuing to charge during that rest period. So it only took so much energy to keep the thing going, but while it was resting, it was still charging. So we don't necessarily want the pulses to be, we want a fast frequency, but we want a longer off time between that. So it's whatever you can practically do. That's why when we did the Ferris wheel, there was quite a gap between each magnets, and so it had an advantage that way. Not just the flywheel mass, but the advantage of the rest period. So I like to talk about that from time to time because rest is needed biologically, but in this situation it actually has some advantages. What the exact relationships are hard to quantify because you have all sorts of variables. So that needs to be, it's a real science that needs to be explored in batteries, what would be the best rate and so forth. So in other words, what kind of time intervals, what kind of rest periods between the switch pulses, you know, so the longer and shorter rest periods, what's the advantage? But ideally, the sharper the pulse, the greater the greater rate of change, the greater the outcome. This is what Tesla talked about 100 years ago with the capacitor, where he was talking about hundreds of millions of horsepower coming from the capacitor being discharged at a very fast rate of change. So we're doing the same thing here because the battery is similar, except we're not discharging the battery that fast, we're charging it. Although the input battery is going to have a pull from it, as as it's pulsing fast too. So that's another subject. So what I said we're going to get to in a moment, I'll say now. So across the MOSFET, drain and source, so the center terminal and the right terminal are those terminals. And so across there is where, if we were looking at a transistor, that's where we put the neon bulb. The neon bulb was for a very low power 12 volt system to indicate, oh, your battery has been disconnected. So stop the motor and don't damage it. But this is not sufficient to protect the transistor that is pushing any more than 25 milliamps. So you can try lightning arresters, but you have to realize those lightning arresters, you have to get them relatively low voltage, below the maximum voltage operating limits of the semiconductor, either the transistor, the MOSFET, or IGBT. So this is kind of an engineering learning experience where you experiment with different parts and you see. So what I'm doing right now is I'm using TVS diodes. I don't have that on there because I'm running this at 12 volts only, and we can look at the spike and you'll see that it's fine at it's still, the spike is under 900 volts, but it's pretty close to the 900 volts. What I want to do is prevent the maximum limit reaching that, because then it will rely on the MOSFET's internal diode. There's a fast switching diode in there, and once you get to that maximum, it will heat up and damage that, and that's where you're going to find your MOSFETs heating up a lot of times, when you're either switching on slow or fast, or that's a different problem, or when you're actually exceeding its maximum limits. I've said many times that many people do experiments and immediately damage their MOSFETs, not realizing that, and they'll never get good results right from the very beginning because they've damaged the MOSFETs. Just as I was setting up here, I was trying some of my 1200 volt MOSFETs, which I had damaged, and I was hoping that I could still use them. I made a real silly mistake, is I changed the MOSFETs to a higher voltage, and then I forgot to change the diode to also a higher voltage. So it was still a 200 volt Schottky diode, which normally comes with the kit. I mean, this is a 100 volt MOSFET, so I didn't need more than 200 volt Schottky diode on there. And so what happened was, when I used the 1200 and 1700 volt MOSFET, I was really causing some problems there, because again, it had nowhere to go, the negative energy, and so everything was heating up and got damaged. And these are simple mistakes when I'm talking on the phone and doing these things. Sometimes that kind of things happen. Those kind of forgetfulness happens. So anyway, I have their 1200 volt Schottky diode that's very fast switching. Both of these are in the lower nanofarad range. I'd have to look up the specs because I have a whole bunch of them here. But there's limited numbers of them, and they can get pretty pricey if you're going to try and do the really fast switching, like down to the 4 nanoseconds, and the higher amperage and higher voltage. They really kind of peak off at 1700 volts. And these are the silicon carbide diodes, the SiC, not just the Si, both for the diode and the the MOSFET. So I'll be selling these on the website, and I can get them for a cheaper cost, so I'll sell them cheaper than what you can buy them normally for. And I guess when I put them up on the website here, when I do this video, I'll put them up by then. So people could replace them if they want to. It's a little bit messy to try and pull out the transistor or the MOSFET from the boards that I've soldered there, so you're going to have to bring it to somebody who knows what they're doing if you're not very good at soldering, because then you could blow out the whole board if you cross the terminals, and don't do it while the batteries are connected. These things happen to all of us when we get lazy. Anyway, so talking about when we look at the oscilloscope, when we exceed the voltage rating of the MOSFET, which will happen very quickly, the more we load down the motor, the more amperage, the higher the spike is going to be, as we'll look. And the more voltage input, the higher the voltage input, the more the spike will be higher, because you're starting with a higher voltage anyway. So we have to put some kind of protection to protect the protection diode inside the MOSFET. And you see this is standard procedure that people have an external diode, and usually you want a lower voltage rating on that diode so that it, well, this is not a regular diode though, we're looking at a TVS diode, is what I should have said. So instead of using the slower switching lightning arrestor, we want actually the TVS diode. And so those have a starting switch on period and a maximum clamping rating. And so you want to actually have the maximum rating of that diode to be lower than the maximum rating of the MOSFET. But all this dampens the negative energy pulse. So this is where you have to deal with a compromise, where you cut it off. And once you cut that off, you're creating a short across the MOSFET. So it's clamped on. So this is where we don't want too good results unless we had a very high voltage switching device, which is, you can get into IGBTs, but usually you only go to the IGBTs if you're pushing more amperage, because they don't operate very efficiently with low amperage, but they do high voltage. So, but the MOSFETs are coming up in voltage, and there's various mechanisms to do switching, but you can't do ideal because it's too costly. Like, this is going to increase my cost about $15 by changing these two parts over from what I've been doing, and I will do that without changing the price up. I'll absorb that cost, but if anybody wants the diodes and the MOSFETs, I'll make them available. And they're also in limited quantity, so I know once I start selling them, people will want to buy them all out, and then I'll have to find another one to decide on. So I think what I'll do is have various diodes or various MOSFETs for the different voltages, but I need some time to decide on all that, and I don't really have much time right now because we've got a lot of orders to fulfill here. But I wanted to mention this to people because I will be changing at least the size of these coils and perhaps the size of the rotors in the next run of parts. So in other words, right now I'm switching at 900 volt MOSFET. That's a very good one. It's 30 amps, I believe, 36 amps maybe. And it is, I think it's about 500 watt dissipation of energy maximum. So it's a really robust MOSFET, and I don't have a heatsink on it. It doesn't need it. I'm only going to be running this at 1 amp. It's going to start up at like 3 or 5 amps or so at startup. We'll look at that. And as it gets up to speed, it's not going to draw very much. So these right now there's very little drag on this. I mean, there's still a magnetic lock here, but it's not nearly what it was. When it's singly spaced, there's a really tight magnetic lock, especially if there's 2 layers on it, and it's hard to turn. So this is kind of preferable. Probably between those 2 spacers would be a more optimum range for the best of both worlds, you know, to produce torque and then also to create some real speed. Ideally, my rotors would be wider, as I said, but then it's not really going to be a mini kit anymore. Like 8 inches instead of 6 inches, so the magnets are more spaced apart, more off time, and less magnetic overlap, field overlap. So really that's what I wanted to describe. And now what we want to do again is focus on ideally what we have done over the years. This is kind of the in crowd, people who were bothered to listen about the negative energy engineering, and who really wanted to follow the instructions. We would give the advice of having, for example, four sets of golf cart batteries, say at 12 volts. So here I have them in parallel, and this is the output from the motor here. I have not yet, I just hooked this up, so I have not started this because while we were starting the video, I was still discharging these batteries with that coil so that the batteries would be very low. And so you can see that the voltage has bounced back up to 5 volts, but the moment I put a little load on it, you would see it drop right back down because there's no capacity. It's just going to rise in voltage because that's how the batteries respond. And anyway, so what we do is we run, so this is the starting battery bank. So this is receiving the negative energy pulse first. And normally when you make a solar system or when you have multiple batteries in parallel, you would connect, say if this was the negative terminal, you would then connect the positive down to the other end of the battery bank, so all the batteries would receive an equal charge through them. But we don't want to do that in this case. We want to run an inverter on the far end, so the inverter is not damaged by the negative pulse, and that by the time you get to that battery, you're not getting the same effect. So what we've done often, if we wanted to rotate the battery around, we would actually always leave it this way, charge and discharge the batteries this way, and then the one battery that's on the inverter, we would rotate around with the front end, and we would put a capacitor across that battery as well. And you can run you could create a filter in there. I'm not going to get into that or show that. It's not my objective to explain all that or do all that at this time in this video. But you can create the same effect when you charge a capacitor with negative energy. You can actually, the other end of the capacitor when you discharge it, its duplicate is positive energy. That's how capacitors work when we do this. So when we would have, if this would be, that would be the rotating bank. So there's 2 sets of batteries. This is one set here, and then there's one behind it. and then the wires loop around and come back out here. And this is where we'll put the inverter on. And so ideally, once these batteries have been converted, we can actually run the inverter while the whole system is running. And then you can do several things. You could either have another source of energy that is very minimal to run the motor while you have quite a bit of an amplifier here, and these batteries charging up a lot faster than what it takes to run the motor. The amount of energy that you can get out of the batteries is much greater than what you can put in, especially with the negative, or really only with the negative system. The positive creates a little bit more energy because there's a negative component to it preceding the positive energy flow. Anyway, what we're talking about here is what we could do is, if we have, what we're going to have here is an inverter here that, this is loose. This one's actually a 220 inverter, and I'm going through an isolation transformer, because if I don't, and I have it hooked up directly to the, if there's no isolation in the inverter, then we have a direct loop with the input, and we can't do that. You can't obviously charge a battery in series with another battery without creating a short across the battery. So you have to have an isolation transformer, and you could then provide a constant current, which I was doing in the video yesterday over here with the setup that I was showing yesterday. I wasn't really trying to demonstrate a proper setup. It was just explaining something where the power supply was keeping a battery charged, and you can do that with a capacitor bank rather than a battery, although a capacitor bank is going to be a lot more expensive than a battery. But ideally, you don't want to just have constant current across a battery without rejuvenating it now and then with proper pulsing. But anyway, if you have a capacitor bank that's a decent size, then this kind of motor requires, surge amperage pulses, and a power supply really can't handle that. They have their peak limits. So you'd want a capacitor bank to even all that out. And it's like a filter cap, so to speak. So really you could run this with, like yesterday I was running this with the power supply. Actually for a couple of days I was running it, charging up one of these battery banks to see the results initially before I would do this video and show 4 of them hooked up, which will be interesting to see. It won't really show you much right now because I've never tried to do that with these batteries. These are my batteries that I've been dragging around to all the conventions, and that's pretty much all I've used them for. So sometimes they've sat for 6 months, and they really should get some rejuvenation, but I didn't really have time to fully rejuvenate them before this video because I wanted to do this video right away. So anyway, going from the last battery set in the line, they're all in parallel, but the last battery set, have the inverter on it, run various loads that it can handle, and then running the input to the input of the of the system. So there's your true closed loop but with an isolation transformer, so that But usually, when you're trying to pulse a battery, this is what I've always said: you can't do this. I've done it over time, but when you try and charge a battery that's running off or where you're trying to charge a battery that's powering a motor, it is very inefficient process because the battery doesn't like to go in two different directions. So you're not going to get the benefits of regular pulse charging, which takes advantage of a rest period, because during the rest period you're pulsing the other way and you're really doing damage to the plate. So I've really talked about not doing that for many years now and get away from the whole Tesla switch that Bedini tried to promote, which was I tried to show where he did admit that it was destructive to the battery in the original Watson device, which was doing the same thing. And it wasn't, Bedini's generator that was flipping from the battery was being charged and discharged back and forth. So this damages the battery really quickly. So that's when he went to the two battery system. But then he still promoted the idea of the Tesla switch, and thousands of people around the world ruined their batteries because he didn't really care. And of course, I've got a whole video on that, but I still draw attention to that. So you don't want to charge, you don't really want to pulse charge a battery that is pushing current unless it's high frequency, which is what Don Smith was doing with quarter wavelength in the wire. And then it was really not doing anything. The battery was really just sitting there as kind of a virtual source. And there was an over voltage potential that was keeping the battery for years in the same voltage, and it was never really being used, except really to start it. It was basically a starter. So on the Don Smith systems that will never be commercially available by anyone for various reasons, on the open market, that's the kind of systems that you do there. But here we're just, what I think is permissible is to sell these kinds of systems which are good enough for the average person. And so we'll do that to a lesser extent, less efficient extent, which is just having a capacitor bank that we supply the current to from the excess in the batteries. So now, before I forget and start running this, to explain what I have explained, and if you go back to one of my earliest YouTube videos that I haven't deleted, which I'll probably delete that one eventually because nobody really cares to watch it anyway, but I do mention it from time to time. So I made this actually a 6-coiler at one point, where there was 6 motor coils on here, and they were 18 gauge wire. And I pushed this harder at 2 amps. So normally this was running at even like 25 milliamps at 12 volts, real low power. But yeah, it was charging quite a bit of a battery bank. So when I did one experiment with the biggest example of how you can get a gain with the bigger the negative impedance or negative resistor, which is the battery, the more output you're going to get. So I decided to use the battery bank that I had in my shop for 3 years, which was 2-volt batteries at 48 volts. So we had 2 different kinds of cell phone tower batteries that had 2,000 amp hour capacities in them. And so this was a ridiculous example of not how you use the batteries most practically, but it's showing you the greatest gain that I've ever experienced with this type of system, with the basic circuit. There's nothing more advanced on this. We're talking, all of this is at the basic level. There's no third stage process, second stage, or any other kinds of tricks or whatever. So what I did was I had, first of all, a 12 amp hour, 12 volt battery, like this little one up here is a 14 amp hour battery, I believe. So a little bit smaller than that. And it was charging identical battery, 12 volts, 12 amp hours. And they were basically charging at around the same rate. You know, what the one that was charging, one was discharging. And then I stopped it, and I disconnected the charging battery, and I hooked up the 48 volt bank of 2000 amp hour batteries. So now these batteries are all in series with each other. So you had the 12 volt battery in series with the 48 volt. And I was not using thick wire, which is a must to get maximum efficiency. Like, I wasn't, here we're only using 10 gauge wire. And then of course it's going to this 1-aught wire or something like that. So anyway, with this little motor, I ended up charging those batteries and producing over 200, maybe to 250 times more energy in those bigger batteries than I would at the same time that I'm charging that little battery. Now, of course, the voltage is not climbing up as fast because we're dealing with a really big battery bank, and it's not going to be exactly the same rate of charging up that little battery as the big battery. But the point is, the amount of total energy that I could get out of those batteries repeatedly over time is way more. And so that's where the negative energy comes in. The bigger the surface area of the resistance or the impedance, well, the bigger the surface area of the inductor, as we talked about in the previous video, or in the battery, the more total energy is usable, let's just say. So again, if you don't use it, you lose it. So if you didn't use those batteries, they would eventually discharge. Not like they would start to discharge right after they stop charging, and then it would still take, probably a couple of weeks rather than a couple of months to like really discharge. And they would go right down to like 9 volts, and people say, oh, my batteries are ruined. So often when I do my one set of negative batteries, the smaller ones that I use at my meetings, they can sit there for 6 months and they could go right down to like 1 volt. And I shouldn't do that. I should be using them more, but they can right away go right up to 13 volts, and then they'll have a higher voltage capacity. You can sit at 14 volts, and then they just have a higher voltage range. It really changes the battery quite a bit, so you have to get used to that. But anyway, they will be pretty good. They can start sulfating too, obviously in the same way, so you have to use them more than I do. Those particular batteries, I forget to, they get stored away in a box and I forget about them, and then it's like, oh no, I should have been charging them. But anyway, the point is that they can go down really low in voltage a lot quicker than the other batteries. The other batteries will still stay at, they're not going to dive below 11 some volts even when they're actually really discharged, because they just sit at that voltage. Like this one, these ones are coming back to, they're slowly working their way up because they still are positively charged. But if I let them sit after they've been converted over to the negative, then, like I said, they can discharge way down there, and you think that they're ruined. And so let me say something that's very important here, which I've said many times. The reason how you can the way you can actually verify what I'm saying is true, at least that there's a fundamental thing that you can prove very quickly, well, as long as you do what I'm talking about here. So it may take you a while to charge and discharge them, but as long as you do like at least 10 discharge and charge rates right down to 0, what people have done is they've tried to put it on another charger, a regular charger, after they've discharged the battery, and it won't take a charge. And they think that their battery's ruined. But all the time that you've invested to converting this battery to negative has to be reversed to make it positive again. And then if you do that, you're going to have to take the same amount of time to bring them back to being negative. So this is something that people can experience, and they can leave their charger on their battery for a month before it converts back to a positive battery, and then it functions all the same. So this is quite a fascinating experiment to do if you really have a negative pulse system here. And so the easiest way is to just make the trigger coil option and run it that way, and then just discharge it with the bulb all the way down till the bulb goes out, and then charge it right back up, and do that 10 times at least, and then you're good. And then try and charge it up, discharge it again, try and charge it up with a regular charger, and you'll see it's just not responding, like it's not putting any usable charge into that battery. So that's one way you can really verify. That's the major thing that people know about, to show them there's a fundamental difference in this battery. What exactly happening? I was talking to a friend today about it. I'm not going to really get into the physics side of it, because I can't see it really to tell you, and it's not my objective to get into that. But it is a fascinating subject people can explore and look into according to their theory of physics, and figure out exactly what's happening there. But why would you have, if it was the same kind of energy, why would you have this situation where the battery is being charged up negatively and is putting out a real load all the way down to zero? You're running this light bulb the same way as you're running a positively charged battery. Now there is different output, and that's another subject I'm not getting into right now, but it's better output. But anyway, you can still run resistive loads and all types of loads. You just can't produce the negative energy charging from that battery. That's the only thing that you really can't do, or anything that would be the equivalent of that, which is really no regular loads. So it will run loads regularly. So here you have this battery that's being used to run regular loads with this type of charging. You discharge all the way down to zero again, and now you try and put a regular charger on it, and it's not taking a charge. You may leave it on there all day and try and run a load off of it, and it doesn't do anything. That should tell you something. And I always get the phone calls from the people that are like, "Wow, Rick, I never could believe it until I saw it." And then those people that don't listen to that and experience this same problem, they'll write some negative review. "Oh, it ruined my batteries," and then I'll get a hold of them somehow maybe, and I'll tell them that, and then they'll realize it, remedy the problem, and then they're like, "Wow, that's really unique, that's really interesting." But the major thing is that they can receive the charge a lot quicker, and there's no losses in the charging. So when you're positively charging the battery, so if you have a cap dump system, the first part of the dump of the cap will be negative and will give you the beneficial gain, which can be, if you were to slowly rise the current up in a slow turn on and turn off of just current from the capacitor into the battery, then a very damped charge, you would get less energy in that battery from the capacitor than if you quickly pulsed it, because the pulse is giving you that gain, a significant gain at the rate, the rate of change. The faster the gradient, the more. So, but all the current that's flowing into the battery is loss. Like, in other words, not all the current itself, but there's always a loss with regular current flow, and that's dissipated as heat loss. So the cap dump system, which we've used primarily so that we could rotate the batteries conveniently, is a gain system from regular current, but it is not as good as just the negative. So if you just had the negative pulse without really the current flow, and this is why your amp meter will show very little indication of current, and that's partly because the type of meters people are using cannot keep up with the rate of change, so you need a proper scope probe to look at all that. But nevertheless, the experiment that we did years ago with this little motor on all the groups was you use a 1 ohm resistor to compare that with a battery. So what happens is a battery's charging and not getting hot. In fact, one of the very interesting benefits of the negative charging is the batteries can be colder than room temperature. I've even had somebody experience their battery freezing in much higher temperatures than freezing temperatures. And the battery doesn't freeze even below freezing temperatures unless it's completely sulfated and it's just water in there. But anyway, that's a rare occurrence. Don't expect to see that or understand that. But anyway, the battery, I've often cold boiled my batteries so that when I measure the temperature with the infrared thermometer here, I see the batteries and all different kinds of chemistries of batteries actually get colder than room temperature. And so the actual sulfuric acid is measured to be several degrees colder than ambient with the proper negative charging. So then that's beneficial because you're not doing the destructive heating process there. And it's showing you exactly that that something different is happening. And I've had people try and explain, some physicists say, oh, well, this and that, and, it's this and that, whatever reason, but the point is it's colder, and that's the bottom line. So you have all this phenomena. There's like 7 or more different characteristics. You have an anti-gravity phenomena to a very small extent, depending on what you're doing, which is what I talked about in the previous video on the subject. And you have all these opposite characteristics. So I was going to say a point, I'm trying to remember now, before I start demonstrating this, and I'm not really going to do a big demonstration, it's just going to show you it running, and I'll talk about it a little bit, but I didn't want to run it so that you could hear me, although I have a microphone, so you can probably hear me pretty good now. So the negative energy allows you to, the efficiency, that's what I was finishing up that subject. So whereas positive energy, you have your losses in charging a battery. So when you think about it, if I have 2 batteries and one is charging at the rate of the other one discharging, and I get the same amount of power out of the charged battery, say a controlled load where we measure the wattage, the watt minutes, watt hours that we can get out of the battery that's powering the motor, and then we take the other battery and we start with 2 identical batteries. We understand their curves, and we start at the identical voltages, and we do this 10 times over, and this is what Bedini did with the TUV company, and I've seen the whole video where they did the demonstration where they did multiple charge and discharges, and they had a gain of almost 12 times more out than the input. And that was, a professional test that was done and videoed. And I think Bearden was there in the video too, watching the whole thing. But anyway, that was an important test. And that was just with very small batteries. But when we do a controlled test, that's why I've always done the 10 cycles, so that you really understand your battery's capacity. You're not dealing with a sulfated battery that's giving you high voltages and no real capacity. Control load with resistive loads that you measure voltage and amperage, and the amperage is the wasted energy. But anyway, the rate of wasting the energy. So one battery is powering the motor, X amount of joules, calculated, added up, and the other one runs X amount of joules into another load. And if they're the same, how do you reconcile that? Because a battery, to charge a battery is a loss. With the internal resistance and so forth, it can be quite a significant loss in not only charging the battery, but discharging it across the load. And there's a whole formula for that at the rate that you're discharging it. And that's dealing with the C rate differences and Puchart's law on that one, but that's another subject. So now you have two batteries, but this battery that's been charged, and they're identical batteries, can actually perform the same amount of work that this one does. Well, first of all, that this battery is being charged at all is remarkable, because nobody's doing that except for people like me. So that's amazing that we have anything here, because normally, like when I showed the fan kit, you've got this fan, and now you're charging a battery while running the fan at the same speed. And it's discharging the battery at the same rate that it was before, and now you're charging a battery. That's great. So that you're charging it all is great, but now if you charge it the same, how do you account for that? You have the duplicate amount of energy here, and that's just with identical batteries under the proper tune conditions and so forth. But now, if you had a bigger battery bank and you do the negative charging, or more of the negative charging, let's just say, or better negative charging, which is again a sharper gradient and less on time, then, and higher voltage, then you're going to have the capability of charging a much bigger bank a lot, well, even the smaller bank a lot more, but the larger the bank, no matter what you do, is going to charge more over time, more power. You're going to be able to now do that same experiment, but you're going to have a lot more runtime, because that battery, you're going to have some different curves there, because the battery's not going to charge up to the full level. If it's a really huge battery and you were comparing it with a smaller battery, it may not get up to beyond 12 volts. But with repeated tests, with your low and high voltages, you can see that, this is what we've done for years, we can get far more energy out with the bigger battery than with a smaller battery. So that's what I'm talking about. That's the negative impedance, negative resistance phenomena. And so, anyway, that's what I wanted to focus on in this video, and that's the reason for the bigger batteries. Now, these batteries are more for the other motor on the ground, the bigger one. This would be a waste of money to try and charge these battery banks really slowly with such a small motor at 12 watts. We're going to be running this at 12 watts. That's not very much. It would take quite a long time to charge these batteries up, but once they're negatively charged, they will respond a lot faster. But still, this is overkill. I would probably limit it to, I would run this, first of all, at a higher voltage, so 48 volts, and probably run it, it usually doubles the amperage as you go up in voltage, capability, but I would dial it back as much as I can tolerate the spike without spending too much on MOSFETs and getting too high of a spike. Then I would run maybe like 100 amp hour batteries rather than 220 amp hour batteries or whatever these are, 200 amp hours, 205s or whatever they are, Costco batteries. But anyway, this is more of an extreme example, especially when I'm only running at 12 volts. So, so I think that covers all that I wanted to say. So let's get started here. So like I said, ideally, once all this is done, I would be hooking up the inverter here down to these batteries here. Before we connect those up, I will just start running this. So let's turn on the oscilloscope. And we'll start this up. And again, I haven't started this yet with these big batteries, so hopefully everything's connected. I made sure of that. But I have let's turn on this voltmeter and look at the voltage. It should climb up to some degree because it's just completely dead, the batteries, because I brought them down to less than a volt. So we have we're going to turn on the thing in a minute, the variac, after I get it going. All right, so I'm just going to give it a spin. So you can see the spike is higher than this probe will allow. We got a 10 times probe on here. I should have had the ammeter on. So we have 2 amps still right now. So now I put the load on it. This light, let's see how bad that light is. I don't want to blind people in the video. It's not that I'm trying to show lights here. I'm not trying to show a load, but you can see, oh, what happened? Huh, now that's weird. I guess oh no, that was, hold on a second. Oh yeah, it's still on, okay. This is a 6.5 watt bulb here. So you can see the spike has come down to, these are 100 volt divisions here. So you can see 1, 2, 3, 4, 5, 5.5, 600 volts. And of course it's reading that maximum and the voltage peak to peak. So this is pretty much at the maximum of this bulb. It's a very strong spotlight, and it's 6.5 watt bulb. And we're only running, well, oh, I know what. So, so we're only at 5.9 volts, and it's climbing on the batteries below. I can't put an inverter on it yet because it's not going to do anything at that low voltage. So we can adjust the on time. So now we're exceeding So now I've turned it up. I'm way higher than the safe operating area of the MOSFET. Now I'm going to be pushing a lot more amps. Of course, we're going to be charging, we're actually charging less because I've increased the on time. So I have now 3.5 amps, and we don't want that. So we're going to turn this down. And speeds up because I have this shorted. And so the battery is going to charge faster now with the less on time. So we'll go right down to, I was running this at 1 amp before. So there's a sweet spot to this one. And again, this is with the double spacing. So this is not normally how we've been running this. And of course I can adjust the Hall too. If I retard it, it will slow down, draw less energy. If I advance it towards top dead center, it's going to draw more current. So there is a sweet spot there. So it's still speeding up like I had it before. So this is where the where when we had the trigger coil, when we were doing the negative energy, it wasn't just it was just really sensitive to the battery's impedance and the voltage input and so forth. So right now we're almost at 1 amp. I'm going to change this back to the 2 amp setting and just place it right here so that 1.2. You know, those clamp ammeters, depending on where you position it. So now we're at 1 amp, just a little bit over. So I just want to keep it where the RPM is not going to dip. And this is why not using a battery on the front end is better, because then it will be a stable power level. So having a cap bank with the power supply, so a DC to DC, isolated DC to DC converter would be saving you, be a lot more efficient than trying to go through like I have in the back here. So I've got a 48 volt cap bank there, 3,000 microfarad, no, 3,000 farad capacitors, which brings it down to 163 or 167 farad total capacitance at 48 volts. And I was going to show all that running, but I don't really need to set that all up right now. That was just for my own purposes later on. But anyway, I'm going to run this at 1 amp. So we're at 12 volts or so on the input battery. We find another meter here. So this is still at 1299 volts on this battery here. Renaissance charged. And so it's not 12 volts, it's 13. And so we have 13 watts here, and we have a nice 400 volt spike. So if you're going to try and replace this MOSFET, you should really have an oscilloscope and realize you should have some kind of clamping mechanism in there that maybe you could switch out, like turn it off. What I was going to do is put a load across the MOSFET so that you would have not just a dead short like a snubber system, but you also have a load being charged. But it's kind of difficult to do that without doing too much, because you can't put a bridge across there, and you can't put a battery directly across there, because then you have a potential that creates a big problem. And I've done that. So you'd have to have a capacitor charging up and dumping, and you'd have to just do it. And I was going to do that for everybody, but I just don't have the time right now to focus on these motors. But I wanted to show people just this part. So anyway, we're charging up this battery slowly but surely. And if I try and increase the power, like I said, it doesn't actually charge it faster. So I can't really turn this variac up anymore because I'm at the limit of that bulb, and it will blow it out. So again, if I go lower, the motor will start to slow down. And then it will kind of come out of a sweet spot and then just dive like that. So right around 1 amp with the double spacing, like I said, gives me over 400 volts. So we're right now at 13 watts, and we're still charging this 800 amp hour battery bank. So going from a 35 amp hour battery bank, which is only running at 1 amp, into an 800 amp hour battery bank, which is, those batteries are still at their maximum capacity, even though they're from 2015. So, oh, by the way, as I was talking to my friend today on the phone, whenever I do the eyebrow kind of certain laughter thing, I'm actually saying something important, or my friend said, well, that's when I know to pay attention. So whenever I get that funny grin, it's just kind of a Freudian slip, I guess you could say. So let's see what else to say here. The other thing that I'm doing now is I'm going to put no wire length between the coils. Like I have this wire length from here where they all come together, and I'm going to put the board right there from now on. So there's no inductance between, there's the least amount of inductance between the coils. You know, so I've reduced that wire. So usually I provide a whole 8 more inches of wire length, which I won't provide now. And then it also means that we can really just attach the Arduino, once you've finalized what you're doing here, you can just use the wire ties through the holes and just mount it right there. And hopefully the programming in the Arduino won't deprogram with the pulses from the motor coils. So it may create too much of an EMP. So you may need to remove them a distance like I was, but for now, I think the Adreno is pretty robust in that, they have to run those under a lot of different conditions, so I haven't had a problem with them so far. So what else do I say here? So we will be having probably a smaller coil set, and they have smaller cores, so that will probably be better for what we're doing. I haven't even tried it yet, so we'll have to get to that soon. And I've got plenty of those coils available. So that's where I'm probably going. Higher voltage input and higher and smaller coils, maybe smaller rotors, reduce the cost a bit so we can make this more affordable. And then we're going to get into the real negative impedance. So I think we'll finally accomplish what this whole purpose was for in this type of motor, which is the negative energy engineering. And then we'll get into, I don't have time probably until the summer to actually produce some products like I was showing in the last video, where I come up with, I think what I'll need to do is make, for those who have this model right here, make a set of coils for different voltages for that system, because quite a few people have that. And then I'll make another set for the new system. And it's very precise. We're dealing with phasing there. So we're dealing with proper phasing and having very exact measurements. These coils are great because they're all exactly the same. And when we first started showing this, we actually were using the old coils, but we actually measured the exact length of wire and wound them perfectly. And that's when you're doing the resonance process, and everything down to a centimeter matters. You have to have everything exactly right. So we have to get everything locking in the RPM, and then making all the coils exactly the same. And then we have to make sure that the input battery doesn't discharge, so that it always remains the same voltage and everything remains exactly the same. And then we run our loads off of the negative impedances, like as a transformer or inductor or whatever. And then we don't have to do this big battery bank system here, but this is the easy way to do it. There's no brainstorming with it. It's straightforward. You can see the charging rate will change, and I'm just going to keep this running until it's 6 volts, so then we can see that it's actually pushed these batteries up to some degree. And of course they'll come back down as I turn it off a bit, but they'll still be higher than when we started. But how many, when you think about it, and of course these are not converted over to negative energy. Yeah, I know I'm changing the subject here. I'll come back to the other subject in a minute, but while I'm remembering, once these are really negatively converted, then these will charge up quite a bit faster. Right now they're sluggish because we've got several things happening. We've got some rejuvenation taking place, which I didn't fully bother to rejuvenate these yet, because I just wanted to do an initial demonstration. And when I make my next charger, I'm going to do that tomorrow, rejuvenate these, and then I'll continue it. I also have to put more water in some of these batteries. Actually, that's what I wanted to mention. Forgot to mention that at the beginning. If you have a sulfated battery, you want to only put enough water in to cover the plates. Don't put any more in until after you've done several cycles and rejuvenated the battery, because the water level will expand. So that's kind of what I was waiting for to put more water in, was to rejuvenate them again, because they've been sitting quite a bit over the years, and I really haven't kept them rejuvenated fully. They're still at the new capacity level, but they are, there we are, 6 volts. They are sulfated a little bit. So anyway, let's, I'll bring up a close-up here of the, I've got to take this off the stand here. All right, so let's look at the details here. So we, oh, now the voltmeter stopped. Times out, saves your batteries. So we can see here, of course the camera lens always changes, but it is a 6 watt. It's upside down, but it's kind of hard to read that one. Or, hold on a second. 5.6 watts or something. Anyway, oops. I think I just closed the cover. Somehow oh, there we go. I accidentally closed the front cover. So, okay, so let's look at the scope here for a minute. So you can see 400, oh, and I didn't show that's just the leading pulse. So let's look at, oops. So you can see the oscillation there, the ringing. So look at the time, we're into the 20 nanoseconds between each division there. So we're at 50 nanoseconds. So that's, this MOSFET can go down to like 30 nanosecond switching speeds. Now this probe is only for 100 megahertz, and the scope is only for 100 megahertz. So I've got a 1 gigahertz that I could pull out if we need to. But once it starts getting really, you start getting like this, to the 5 nanoseconds, the probe can't keep up with it. So anyway, you can see here the H wave, but it's so, so there's your ringing, your oscillation there. So you can see it lower and higher. So you got a little bit there. And then you have not your regular H wave. So you can see this on time is very short, right? It's relatively short compared to the off time. But there is still a spike, is what I'm saying, on the on time as well. Now the thing about it is, oops, you can't really see with this scope the downward spike until I get down to the low voltages. So I need to, if I had it with the other oscilloscope, the faster oscilloscope, the faster probe, you can see more of the negative going spikes. But you can't see them when I go to the higher voltage. Anyway, you can see the frequency the speed that it's running at will around 400 hertz, which is great. Really what we want to do is get some core material that is for 400 hertz transformers to run as our third stage process, instead of like 60 hertz or the high ferrite. So anyway, here is very rapidly charging up that battery bank. No, not quite, but it's not expected yet to be charging it fast. And of course, you still have the bounce back with the, see even here, it's showing 600 because this is hard to actually reset and get it just at the 1 amp level there. So that's more accurate there. So let's look at this. So here we have, now I've just added this so I could replace the MOSFETs without having to solder them. So this is the potentiometer that I was talking about, and I have it turned down probably halfway. Now we set in the code, in the Arduino code, we program it to have a certain on-time max. And right now, it's really too high for this particular setup, because as you saw, as I go any higher than this, it starts to bog down the motor and the charging rate isn't as good. And also the output from this, the generator coils here going into the variac, right? So here I'm kind of going at opposite, like I've shown in other videos. The input is going into the output, and the output is the input cord, so that we can start at the 0 and work our way up. So anyway, I was saying on the board here, if you put one of these terminal strips on there, then you can replace your MOSFET when you need to. And you can see I'm going across the drain and the source terminals for the probes. And this is the Schottky diode there. So these are about $14 a piece, I think, somewhere around there, $15. They're pretty expensive because they're the state-of-the-art. They're really, really good. Oh, and so it's a big mess here because I've soldered and unsoldered this many times, and I'm just throwing it together quickly, so it's not, it's Rick's mess of wires. So you can see that the magnet would really correspond with that corner post. So we are actually quite retarded here on the timing, quite a bit after top dead center, because you can see really the coil, where the coil's positioned would be the top dead center. And we'll have to move that over more and more in this direction when we rotate this clockwise with the higher voltage. So we have a gate driver here. I also have another gate driver, but the pin orientation is different, and it's faster yet than this one. But this has been a very good, robust, it's a 12 amp gate driver, so I use that on my bigger motors, these ones down here, to switch multiple FETs, at least 2 of the big FETs. So the FET that I was using in my previous motor, some people are waiting for some of the big motors, and that's because I wanted to work out a better FET here. So the FET that we're going to be using has half the resistance of the other FET, and it's faster. So, and it's a little bit cheaper too. So that's an improvement that I wanted to upgrade the bigger motors on. And right now there's only this motor, the other ones are not available. So let's look down here at the details. So here again this is the Arduino battery. This just runs the gate driver and the Arduino, and this is just a isolation transformer that this is going into. I can't run that inverter off, well actually I don't have even a load here to run, like this is the output and not the input, because that's just the way I have that isolation transformer set up. Usually I go in the other direction from 110 to 220 when I make my battery chargers for 220. I use that, but in this case I was running a 220 pure sine wave inverter, so I just ran it backwards through there. So there's my big Maxwell cap bank, and then here we have the battery bank, and you can see what I did here is I made the battery cable run through it, through one of those big terminals that the whole wire could fit through, and I stripped the wire around it, and it's kind of awkward to put the nut on a bit, so you kind of do these batteries, connect them up one at a time, but that way I don't have to run multiple strands of wire, which then creates a little bit of a loss. And this way, now if I ran out of this big wire, so I would have actually wanted to run this all the way up here to right there. But this is just a temporary thing to show a basic demonstration. And then of course I have the same thing down here. So this is the terminating point. So you can see, let's see if I can, so this is that one terminal, and then the other one is back there. I don't seem to put a light on this, but let's look on the other side. So there's the front one, and the back one is back there, and then it goes up around. So you can see it just loops up around there, and there's that Maxwell battery here, or a capacitor bank. So you can see here the Variac, sorry I'm doing the shaky camera syndrome, 13 volts on that. And now we're at 6.1 volts and climbing. So let's turn it off and see. I usually turn it off just by disconnecting the clip on that battery, the small battery. So you can see the amp meter is still showing some amps, so it wasn't really quite at one amp either. It was probably 900 milliamps. So you can see that the battery, okay, first of all, the light is still going until it stops. So it's still, the generator coil puts out, even just with getting this, right. So this is no motor action here, like obviously it's not taking any power from the battery to do this. Like I can disconnect the battery and you still have, so that's the regular generator action apart from the EMP benefit. So yeah, here we have the voltage kind of holding out. It's not going up anymore, so we know the battery is not, it's kind of stabilized from it being discharged so low. And that was the major point of my video yesterday, was that if I was going to try and illustrate that, but then I realized I had to, before I ran the motor, I had to talk about things for a long time, and I wanted to show the battery voltage coming back up, so I didn't want to cheat as people do, like I was showing yesterday, revealing that in that video, where if I had loaded this down, that's kind of one of the reasons why I'm doing this video. That was one of the motivations to talk about it again in a more vivid way, where drawing these down to 1 volt for a while and holding it there, and then, well, actually not for a while. If I had done it really quickly, drew them down to 1 volt, and then disconnected it, started the video up, and then didn't show you the voltmeter until I was ready to start the motor, then I could really trick people. And I always deliberately leave my voltmeters on so that people don't think I'm playing that kind of game. And so what happens is you do that, and the battery, and then you run a load, like say you do that on your input battery is what I would be doing instead of the opposite of what I was showing. But if I was to even do it this way, the battery was bouncing back naturally, and I would say, wow, look at the charging rate. I'm charging 800 amp hours of batteries, and look at the voltage rise so fast. That's like a real gain, like, wow, what an over unity system. And how many videos have we all seen where people are playing that game? But on the same way, if I did that on the input battery, where I loaded it down, and then I was running a very small load, and then saying, see, look, this is back looping, it's charging itself up, because look, the voltage is rising. And you're just scratching your head saying, oh, there must be something there. But the real reason is that you are, see, look, the battery is still, now it's starting to rise again. It went down, and now it's going back up. It's interesting as we're talking. So, yeah, that's quite interesting here. Obviously not at the rate that it was going up while I was running it. But anyway, that's why I run these videos longer and I talk afterwards. Not that I like talking or anything, but then you can see it climb because of the motor. So you could still probably have a little bit of charging continuing on, because I mean there's very little of a conversion yet in the system. You have to go all the way up and down multiple times, and there is some negative charging in these batteries from all the pulsing that I've done, but not nearly as what we're doing here with the really high spike and the very short on time. So I think that covers everything I wanted to say, and I hope this helps people. But you can see one way to really focus on the negative output here is to do it with batteries. And then we'll get into the other stuff later on when I get a little bit more time, and to source out all the parts and make all the measurements and all that. So, so anyway, thanks for watching. I hope you enjoyed it.